So this is going to be your even and odd identities, or even identity for cosine, your odd identity for sine. So if we go over here and we draw ourselves a unit circle, this may not look like a circle, but I promise that it is. And again, we draw the 1, 0 here to let us know that it's, well, to illustrate that it's the unit circle, because any radius in the unit circles could be 1. So let's say we have an angle here from 1, 0, right? Because on the circle, that's where we start our angles from, the x-axis here, positive x-axis. And then we'll say this angle is the same angle. It's just going the opposite direction. So we'll call it negative b, right? This actually goes up here, not right here. So knowing that we can write ordered pairs on our unit circle, instead of x comma y, what we can do is we can write them as cosine of some angle. It doesn't have to be theta, but that's just what the just like the generic form of it is. But it's just going to be some angle. Cosine of some angle is your x value. You can represent your x value, and then sine of some angle can represent your y value. So what we can do for this order pair right here is we can rewrite this as cosine of beta sine of beta, right? Because beta is going to be our angle, so cosine of beta will give us that x value. So down here we can write this as cosine of negative beta sine of negative beta. So then from here, if we look at our graph, and now any graph like this, any Cartesian coordinate system uses, it's also called a rectangular coordinate system. Why is it called that? Well, usually it's drawn in a grid, so you can go, you draw a rectangle to the points, right? So so you go one direction, then another direction. So from here, I followed the x-axis, and then up to our cosine of beta comma sine of beta point, and then down here I did the same thing to get to our cosine of negative beta sine negative beta point. So if you look at the paths we took, right, we went across and then up, and then for the other one we went down. But for both of them, right, we went the same distance across, or we traveled the same path on the x-axis, right? So that is how we know that cosine is even, because whether the angle is beta, whether the angle is positive or negative, the output is still going to be the same x value. So we write this as, well, the definition of even is, of even function is f of negative x equals f of x for all x in the domain of f. Right. So for cosine, it's cosine of negative theta in this case it's beta, so we'll just rewrite that as beta, equals cosine of beta for all beta in domain of cosine beta. So because it's traveling the same path, right? Now our definition for an odd function is f of negative x is equal to negative f of x. So if the input is negative, the output's going to be negative. And that's, again, that's for all x in the domain of f. So if we look at our graph again, we'll see these two travel the same distance. The only difference is that they're in the opposite direction, right? So you go the same x, and then if it's the positive angle, you go positive, and if it's the negative angle, you go negative. So here we can tell that for this, because the y direction again is the sine function. So from there we can tell that sine of negative beta is equal to negative sine of beta, right? And we can see that here because it works, because if you go here and negate it, and I'm sorry, if you go here, it's the same thing as this y value. This y value is the same thing as this y value negated, or the opposite of this y value. So sine of negative beta is equal to the opposite of sine of beta. So if you have this y value, and it's positive up here, right, because the second quadrant, you make it negative, it'd be right here, down here in the third quadrant. So that's why this works, and that's for all the domain of sine beta. Right, because I mean, if the angle wasn't in the domain, it wouldn't really work. So that's why we write that part. And that is the proof of the even and odd identities.